Mobile telecommunication is an essential part of the infrastructure in our modern societies. However, mobile networks consume a considerable and rising amount of energy. Of course, this large energy consumption presents challenge, both from an operational cost perspective and for environmental concerns. In this video, we will show how we have accomplished the results by highlighting the main assumptions and the methodology that we have followed. The Mobile Working Group concentrated its activities on technologies that would enable the radio access network to provide, in the most energy-efficient way, full coverage and the capacity and performance that will be needed in the year 2020. Within mobile networks, these consumes the largest amount of energy. However, not only is the power emitted over the air relevant to energy efficiency, but so is the energy consumed by the equipment for data processing, backhaul, cooling, etc. We have taken all this into account as we develop the main technologies that are at the foundation of the potential energy efficiencies in 2020. But how did we calculate the energy efficiency of a mobile network? Our working group developed a methodology to measure the energy efficiency for a nationwide network and benchmarked all proposed approaches by using this toolset. The energy efficiency of mobile networks depends on the usage patterns. Just as a car burns gasoil at different rates depending on whether it is traveling at high speeds or idling at a traffic light. So, we measured the efficiency as electrical energy spent per transmitted data volume averaged over a period of time, in joules per bit. And for the efficiency of a nationwide operator network, we averaged the energy spent over a wide span of deployment and operational conditions, from busy hours in metropolitan areas down to rural areas at night times, with very low traffic demand. We analyzed network traffic patterns and defined a representative traffic model for all these cases, including also the anticipated near exponential rise in mobile data traffic by a factor of 89 between 2010 and 2020. From network traces, we derived user densities in urban hotspots and determined the data volume transferred per session. Understanding these patterns is essential for an energy-efficient deployment of wireless equipment. Simulations for network energy consumptions critically depend on a realistic insight in hardware power consumption in different base station architectures. Therefore, we built a power model for a broad variety of base stations. We have built a new reference model for wireless research that considers in detail the RF chain and baseband processing, power supply and cooling. This complementary set of models now allows us to anticipate the network behavior for all kinds of deployments, for example for the massive rollout of small cells or for futuristic base stations with hundreds of antennas or new management schemes with intelligent sleep modes. With this powerful simulation framework, we can compare different research directions for network energy efficiency, compare different scenarios, and find the minimum network energy consumption and the associated set of architectures, technologies, and management protocols.
Unlike traditional architecture, our BCG2 project uses small cells and then completely separates the signaling and data functions at the wireless interface. With the reduced distance between the network and the user terminals, these small cells will consume less energy than traditional macro cells. We will need much more of them, but at any given time, a lot of them can be deactivated since they are not serving any users. By separating the signaling and data functions, they can be turned off and on when and where needed, making the energy consumption proportional to traffic load and the energy efficiency extremely high. A A separate infrastructure for signaling provides continuous network accessibility with full coverage so that communication services can be requested at any time by users. Signaling data rates are normally much lower than user data rates, so the signaling infrastructure can be designed for these, resulting in greater energy efficiencies.
So LSAS stands for Large-Scale Antenna Systems. It's also called Massive MIMO. The way the system works is your base station is equipped with a large number of physically small, low-power, individually controlled antennas that work together to direct a multiplicity of data-bearing beams to a large number of users. And if done properly, each user gets what's intended for him with virtually no interference due to the other transmissions. This is very energy efficient. Every time I double the number of antennas, the selectivity of my beams gets improved by a factor of 2, and I can deliver service to the users of the same quality as before with half the total radiated power. Or putting it another way, what Massive MIMO does is it sends power where it's needed and doesn't waste it by sending it indiscriminately everywhere where it can only cause interference. Now there's a trade-off involved though. An increasing number of antennas will improve my radiated energy efficiency, but internally extra power has to be expended on a larger number of electronics chains. There's also more computation that goes on, and there's power consumption associated with computing as well. So we have this trade-off. Our research has addressed the problem of how do we come up with an optimum system. Too many antennas, you have great radiated energy efficiency, but high internal power consumption, and the converse if it's too few antennas. So for a variety of scenarios, we've performed this optimization where you have a cell size, you have a stipulated level of service, and now you want to choose the optimum number of antennas, the optimum radiated power out of each antenna so that you give the required service and at the same time maximize the total energy efficiency. The results are very impressive. So in a rural scenario where traffic is rather low, user density is low, but the cells are very big, we get a 1,600-fold improvement in total energy efficiency over the 2010 reference. It's even more dramatic for dense urban, where you have relatively small cells, many users, and therefore very high traffic. There, the energy efficiency improvement is 14,000. So we're extremely pleased at this outcome. We never anticipated quite that it would be this great, and we think that LSAS is a great candidate for fifth-generation wireless technology.
Spectrum efficiency, defined in bits per second per hertz, is the key indicator of how efficient bandwidth is used. Energy efficiency, defined in bit per second per watt, is the key measure of how efficient energy is consumed. It's interestingly suggested by the groundbreaking Shannon law that there is a fundamental trade-off between the energy efficiency and the spectrum efficiency. The GTT project explores these relations for the energy-efficient transmission technology design. Our first idea is to expand the bandwidth so that the transmit power can be greatly reduced. Dedicated signal processing algorithms at the receiver end to maintain the reliability of the whole system for low power transmission is thus a very important contribution of the project. And then we extend our research into the multi-user, multi-cell scenarios where we find that the story becomes more challenging and interesting because of the presence of interference. And we further find that reducing the interference can improve both the energy efficiency and the spectrum efficiency. So the GTT architecture knocks out the strongest interference by interference alignment, and we use the dynamic MIMO strategies together with the antenna slipping to maximize the network energy efficiency given the spectrum efficiency requirement. And on top of this, we use the collaborative distributed antenna systems to support low interference and low power access. Together, more than 6,000 times of energy efficiency improvement over the reference architecture 2010 is available from our project.
Bringing these huge research efforts together, we have been able to provide guidelines on how to build the most energy efficient mobile networks. The GreenTouch mobile architecture is created by selecting the most energy-efficient GreenTouch technologies on top of the basic scenario, separately for each deployment area, such as city centers or countrysides. For this architecture, we calculated the overall energy efficiency for a network including all developed Western countries with our simulation framework.